Hey everybody, we're going to talk about standing sound waves today. Now, before you watch this video, I do want you to watch the video I linked in the description down below. This is a video from Utah State University, and I recently discovered their channel. They do a lot of good physics demonstrations in that, so he's going through some organ pipes and how they work. So check that out and then come back to this one. So anyway, standing sound waves. We learned about standing waves on strings a week or so ago. And standing sound waves work on the same concept. You know, a string, we send a wave down the string, it gets reflected back on itself to create that standing wave. Standing sound waves are pretty much the same thing. Now, one common example of standing sound waves is musical instruments. So a trumpet, a saxophone, a flute, any wind instrument works on this principle. Now, they get pretty complex. So in high school physics, we usually simplify it to just an air column or a pipe or a tube. So my resources at home are a little limited. I couldn't find anything, so I found this, a little paper towel roll. Okay, so this is an example of what we use in class, but a little more sophisticated than a cardboard paper towel holder. So anyway, if you can imagine, I'm going to close one end, and then we send a sound wave in this end. It's going to get to the closed end and reflect back on itself, just like a string. Okay, now it also happens when both ends are open as well. So when a wave goes from one medium to another, some of that wave will get transmitted through into the other medium and some gets reflected back. So even though this is an open end, there we go, an open end, it's still a separate medium out here in a sense, because the air is less restricted, it's more restricted in here. So you will get sound hitting the end, some gets reflected back on itself. When conditions are just right, and we'll talk about that in a minute, you get that standing wave, which is resonance, okay? So that forced vibration, which is the reflected wave, matches up with the incident wave. We get that big amplitude, that loud tone. So let's take a look at a simulation to see how these standing waves are created. All right, here's the simulation. I put a link to this in the description as well, so you can check it out on your own. First thing we're going to look at is with one side open. So this is the open end, this is the closed end. So it'd be like, you know, if I've got the tube there and I close this end off and I send the sound into the open end. So the sound wave is coming in here, bounces off the closed end, gets reflected back. If it's just the right frequency, just like with strings, it will overlap itself and create that standing wave, a loud sound. Now, at the closed end, that's where the molecules are restricted from moving. So that would be a node there. You see those molecules aren't moving at all. At the open end, they're free to oscillate in and out as much as they can. That's an antinode. So this first graph is showing that. It's the displacement of the particles. So you have a node here at the closed end, an antinode at the open end. I'm not going to address this other graph, so don't even worry about that. Now we can increase the frequency. So if you increase frequency, speed doesn't change, right? If you increase frequency, the wavelength decreases. So we're going to take this wave and kind of squish it down until the next antinode gets to the open end. So like that. Okay. Now, I'm showing you the closed end. That's not really our focus today, but I think it makes a little more sense once you see the closed end. So now I'll do both sides open. This is what we're going to talk about today. So at the open end, we're going to have an antinode. So an antinode here, an antinode there. You can't have a node there because it's not restricting the particles. It's an open end. So what happens with your standing wave, you have a node right in the middle. And this is where the particles then are not moving. So this is the lowest frequency, it's the biggest wavelength, so the lowest frequency that will fit in this situation. We can increase the frequency, and you see when we increase the frequency, we decrease the wavelength, so we squish that wave down until the next antinode gets to the end there. So now we've got two nodes in the middle. Okay, and then we can keep going on from there. But that's basically how a standing wave is formed. Think back to strings, it's the same concept. Even when it hits the end, a fixed end, it gets inverted. A free end, which is this case, it does not get inverted. It all lines up. We get that standing wave, which is resonance, and we'll get the loud sound. Okay, so now let's look at some math involved with these. Okay, let's review some things we already know about standing sound waves. So when a wave goes from one medium to another, Move my out of the way there. Some energy is transmitted and some is reflected. We just talked about that. Displacement nodes are at closed ends. That's where the molecules are restricted from moving. Displacement antinodes are at open ends. That's where they're free to move back and forth quite a bit. So similar to standing waves on strings, only certain frequencies will produce standing sound waves in a given length of air column. And that's what we're going to look at today. So there are two types, open at both ends, like a flute, a recorder, or an organ, like the video you just watched. And then the other type is closed at one end but open at the other end. So this would be like a trumpet or a clarinet or something like that. Okay, so first up, we're going to look at the lowest frequency that will create a standing wave in an open-end air column. So again, lowest frequency means biggest wavelength. So we're going to stretch this wave out. We know we need an antinode at each end because they're open at each end. So it's going to look like that. Okay, now next we need to determine how many wavelengths we have here. So we've done this a little bit. The physics classroom exercise you did incorporated this. So again, we're just going to look at one side of it. We start here, we end up there. That's going to be a half of a wavelength. Or we can say the wavelength is 2 times the length of that pipe. Okay, now using V equals F lambda, where lambda, the wavelength, is 2L, we just substitute that in there. And now we're going to solve this for the frequency because we want to know the frequency that will create the standing wave there. Okay, so this is going to be V over 2L. So V, again, by default, 343 meters per second, unless you're told otherwise, and L, the length of the column there. So this F1, I put the subscript 1 there, this is called the fundamental frequency. It's the lowest frequency that will create a standing wave in this particular air column. It's also known as the first harmonic. You may have heard that phrase before. Okay, so the next one, we're going to increase the frequency, so we decrease the wavelength. So we're going to take that wave and we're going to squish it down until the next antinode gets to the end there. So it's going to look like this, okay? This used to be the end, we squished it down, now the next one. So we've increased that frequency. So how many wavelengths are here? Looks like 1. Okay, so the wavelength is the length of the pipe. Using V equals F lambda again, it might have to move me out of the way here. Well, we'll see. Okay, so using V equals F lambda again, where lambda is length of the air column, and then F2 is V over L. So if we just solve this for F, we get V over L. V over L is the same as 2V over 2L, and if you compare it to F1, you can see it's just double that. So F2 is 2 times F1. This is the second harmonic. So let's increase the frequency again, squish that wave down till the next antinode hits the end there. We'll have a pattern that looks like this. Now, one thing I want to remind you of is sound waves are longitudinal, okay? But it's so difficult to draw a longitudinal wave in a situation like this. So we depict it as these, the particle displacement, so to speak. So anyway, we've got this picture. How many wavelengths are here? Start here. There's 1, and there's another half. So it looks like 1.5 or 3 halves. Okay, or you can say the wavelength is 2/3 the length of this. And some people look at it and say, okay, here's one wavelength, that's 2/3. Jump right to that, that's fine with me. Okay, again, V equals F lambda. So substitute the 2L over 3 in for lambda there, and you get V equals F times 2L over 3. So solving that for frequency, we get 3V over 2L. Compare that to the first harmonic. That is 3 times the first harmonic. So yeah, this is called the third harmonic. You see the pattern? Okay, let's do 2 more just to make sure we've got it. So increase the frequency again, squish that wavelength down again. Here's our next pattern. We can count how many wavelengths are here. 1, 2 full wavelengths here. Okay, so the wavelength is half the length of that air column. V equals F lambda, plug in L over 2 for lambda. There's our expression. Solve that for frequency. We get 2V over L. If you multiply top and bottom by 2, that's 4V over 2L. Compare that to V over 2L, that's 4 times F1. So what do you think we call this one? That's right, the fourth harmonic. Okay, the last one, we're going to squish that wave down again. So we count the wavelengths here. We should get 2.5 wavelengths. Okay, double check me on that, 2.5 wavelengths or 5 halves. So the wavelength is 2/5 the length of the pipe. V equals F lambda. I'm going to move me out of the way real quick. Okay, V equals F lambda. Plug in 2L over 5 for the wavelength, and there we go. And then solve it for frequency. We get 5V over 2L. Compare that to V over 2L. That's 5 times that first harmonic, so this is the fifth harmonic. All right, so they're all multiples of that first harmonic, which is very convenient for problem solving. Okay, so to sum this up, you have displacement antinodes at the open ends. Any harmonic, if you want the 18th harmonic, you just take 18 times the first harmonic. It's just the multiple of the first harmonic. Okay, all harmonics are present, 1, 2, 3, 4, 5, 6, 7, 8, so on. I recommend you always work with the first harmonic. Couple of reasons. One, it's easiest to draw. If I gave you the 18th harmonic, it's going to take you a while to figure out how to draw that. So just draw the first harmonic. If you need the 18th, you know that's just 18 times the first harmonic. Least confusing. Okay, so let's look at a quick example here. All right, so, oh man, I'm always in the way here. All right, so the air in a 1.7 meter long open end pipe. So it's like the paper towel holder, 1.7 meters long, resonating in the third harmonic at room temperature. Determine the frequency of waves. So what we have is we've got a sound wave going in one end. It's going to reflect back. We're hearing a loud tone on that. So that's the resonance. That when it says resonating, it's creating that standing wave, that loud tone. And it's the third harmonic. We need to keep that in mind. So like I said, let's start with the first harmonic. So draw a picture of the first harmonic. There we go. It's always going to be the same. Pretty easy. Okay, so we know the wavelength is 2 times the length of that tube. We use V equals F lambda, where 2L is the wavelength. So we just substitute 2L in for the wavelength here, and we get V equals F times 2L. Okay, so here's just a reminder, our picture is for the first harmonic. So this, when we solve this for frequency, that is the first harmonic, okay? We need to remember we're on the third harmonic, but hold off on that. So we drew a picture of the first harmonic, that's what we're working off. When we solve frequency, that is the first harmonic frequency. All right, just move myself over here. That should be good. Okay, so when we're not given the speed of sound, like in this case, we're told it's room temperature. By default, we're going to use 343 meters per second. That is the speed at room temperature. Oops, and I cut that off in the middle of. Okay, and we're also going to use the given length of the pipe, the 1.7 meters in this. Okay, so we plug things in here. The speed is 343, just going off of what we had here. The length of the pipe 1.7. So the fundamental frequency, the first harmonic, is 100.9 hertz. That's not what we're looking for because it says we're in the third harmonic. So we just have to take one more step here. How do we get the third harmonic if we know the first? That's right, just multiply it by 3. Okay, so then there's our answer. So in this situation, we've got a 1.7 meter long, open at both ends. If we know we're at the third harmonic and when we hear that loud tone, that frequency must be 302.6 hertz. Okay, so that's it. As always, let me know if you have any questions.